Well, good evening, everyone, and welcome to another special evening for our graduate program in Urban Development and Design at the Faculty of Built Environment, and a very much a special evening for our university. And as always, when we start these events up here in Leighton Hall, we acknowledge the Medical people who are the traditional custodians of this land. We pay respects to their elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who are here this evening. Well, for those of you perhaps who don't know me, I'm Professor James Werrick. I'm the director of the MUD program, as we call it, now in our 24th year, and we have been hosting the Annual Paul Reid Lecture in Urban Design for the past 12 years. The lecture is named for our great friend, the late Paul Reid, who was a foundation member of our graduate program, former chief architect of Canberra, and immensely knowledgeable of the world of practice, and it was a great loss when he died quite prematurely, really, shortly after he retired. And so we've always been delighted to honour him in this way. And it's also in the Utzon lecture series, the year started off with a very exciting Utzon lecture series from Flores and Prats from Barcelona, but we always had that role as the first one, but I still think that it's a special time in the year when so many of our friends from practice come and meet and catch up with what's been happening over the summertime and find out what's taking place in our world of city making in Sydney as the year ahead of us unfolds. So it's really extraordinary achievement on the part of our wonderful students to have put together this night, with the help of our UNSW events team, to put together the yearbook, which I will talk about at the end of the proceedings, still sponsorship opportunities, and also, of course, the special exhibition that we'll welcome you all to at the end of this wonderful lecture. So what makes it possible is indeed our sponsors, and we truly thank them, and we're honouring them here in our first slide. So Scott Carver have made a 3-year commitment to supporting this special evening, and that really makes it possible for us to start planning very early on what we can do. Bates Smart, truly wonderful supporters of ours. In fact, the first year we sought sponsorship, they came forward, and that was 10 years ago. So 10 years of commitment to us is something that we deeply, deeply appreciate. But in fact, we appreciate every one of our sponsors. And so we also have Group GSA, very loyal to us in so many ways, and great to have them this year. From China, we have Jianfeng Engineering Cost Control. Great to have so many connections into the world of practice across the world, and in this case, of course, in China. Johnson, Pilton, Walker, again, wonderful supporters of ours, with Professor Richard Johnson, of course, as part of our emeritus and distinguished alumnus. Architectus, great supporters of us, and not only as sponsors, but also my good friend and colleague, Brendan Randall, who's a senior architect there, does an enormous amount of teaching with us, including taking our students overseas now for the 2nd year in a row when we went to Japan this year. Pascal Bobillier, who's a graduate of our program and has always been supporting us in recent years as his practice has developed in interesting and unusual and fascinating ways. Dixon Rothschild, very much committed to the MUD program for so many years. Nigel Dixon taught with us and has brought great opportunities to us in terms of our design studio possibilities, and many of our graduates have worked with Dixon Rothschild. Habitat Planning, again, an alumnus, our wonderful friend David Hunter from Albury, Wodonga, who supports us each year. LFA, Lester Firth Associates, once again, wonderful to have Alf Lester as one of the really senior urban designers of our city supporting us in this way, but also an associate at the firm, Carla Mamarol, who is a graduate of our program and who teaches with us in a number of our courses. Urban Concepts, which is another very loyal and devoted supporter of ours every year. and a very good friend, David Wolski from Wolski-Koppen, who graduated in architecture here in the 1960s. I'm sure he won't mind me mentioning that. And very wisely came back and did the MUD program for CPD points. Incidentally, tonight is also a possibility for CPD points, and if you want to sign up for it, there's a table outside. And so please take advantage of that opportunity for those of you who need to get your CPD points every year. Then in addition, this year we're delighted to have as a donor, Yu Hong Chao, who's wonderful that she has been able to support us as a donor. And in addition, we have a very, very generous and wonderful friend of ours who's an anonymous donor who has really made the whole event possible tonight. And we truly, truly appreciate that great level of support. I'll talk more about what we've done in the MUD program at the end of the evening, but first we have the Paul Reid Lecture, and to introduce our speaker, please welcome to the stage our Dean, Professor Helen Lockwood.
Hello and welcome everybody. I'd like to welcome all our students, our alumni, our staff, our industry partners, and of course our sponsors to this 12th Annual Paul Reid Lecture and another one of our great Utzon lectures. And it's great to see the Leighton Hall completely full to its gills for this extraordinary event. In our faculty, we are very much focused on cities and urbanization and the impacts of urbanization. And so in everything we do, we focus on shaping future cities that are resilient, inclusive, livable, and sustainable. And so it goes without saying that our education and our research is both broad and deep. It is collaborative and interdisciplinary. And so we hope that through this lecture, you will see this demonstrated in action. So it is with great pleasure that I introduce the speaker for tonight's lecture, Scientia Professor Mattheos Santamouris, the Anita Lawrence Chair in High Performance Architecture at the UNSW Faculty of Built Environment, who, in my opinion, exemplifies our remit, working across scales, across disciplines, and addressing our most pressing urban challenges through his research. Professor Mattheos Santamouris is an internationally renowned scholar in the area of high-performance built environments. He has spent more than 20 years investigating urban overheating around the world. In addition to his role at UNSW, Matt has a range of prestigious appointments, including visitor professor roles at major universities, including the Cyprus Institute, Metropolitan University of London, Tokyo Polytechnic University, Bolzano University, Brunel, and National University of Singapore. He is the editor-in-chief and member of the editorial boards of many esteemed journals, including the Energy and Buildings, the Journal of Advanced Building Energy Research, the Solar Energy Journal, International Journal of Solar Energy, Journal of Buildings and Environment, Journal of Sustainable Energy, Low Carbon Technologies, and more. He's the editor and author of 15 international books on topics related to urban heat, solar energy, and energy conservation in buildings. And as well, he's edited a series of books on buildings, energy, and solar technologies published by Utzon in London. Furthermore, he's the guest editor of over 12 special issues of various scientific journals, and as the author of almost 290 scientific papers published in peer-reviewed international scientific journals. And he is a reviewer of research projects in over 15 countries. It goes without saying that he is one of the most highly cited researchers in his field, according to Clarivate in 2017 and 2018. That is no mean feat. So it follows that earlier this year, the University of New South Wales bestowed on Professor Santamouris the prestigious honour of Scientia Professor in recognition of the global significance and impact of his research and contribution to his field. In celebration of his appointment and to this esteemed role, Professor Santamouris will speak on cooling our cities. He will present a provocative and timely analysis of advances in science and design for the mitigation of urban heat, a vital challenge for 21st century city making. in the face of rapid urbanization worldwide. Rapid urbanization is a new UNSW grand challenge that our faculty is leading through collaborative, interdisciplinary work of academics across UNSW and more broadly. Professor Santamouris will share his recent world-leading research into urban warming in Western Sydney, the urban heat impact of the Western Sydney Airport, as well as urban heat mitigation studies of Darwin, Adelaide, and other cities across the globe. So please join me in welcoming Professor Santamouris to the stage. Thank you.
Thank you, Helen. Thank you, James. Thank you very much for the very kind invitation. Ladies and gentlemen, what is special with the urban climate? What is happening in our cities? In reality, the thermal balance of our cities is positive compared to the thermal balance of rural areas. Why? Because we have a lot of heat generated in cities because of the anthropogenic heat, because of the very high density that absorbs solar radiation, because if thermal radiation that is emitted by our buildings, by our, let's say, infrastructure cannot escape because of the canyons, and because, you have pollution that absorbs the solar radiation and the infrared radiation that is emitted, by our structures. So this contributes to increase the temperature of our cities, and in reality, we have a phenomenon which is known as urban heat island, where, let's say, the temperature in the center of the city or in the very dense areas of the cities is much higher than the temperature around the city. This is the more documented phenomenon of climatic change. We had the very first measurements in 1902 in London, where they have understood that the temperature downtown London was about 3 to 4 degrees higher than in the surrounding area. Now, we have more than 400 cities around the world where we have documented, let's say, data that shows really that there is a tremendous overheating of our cities. On the other hand, a part of the local climatic change, because of the positive thermal balance of cities, we have the so well-known global climatic change, which is because of the high increase of the CO2 and the other greenhouse gases concentration in the atmosphere that contributes to increase the temperature. The global climatic change increases as well the temperature of our cities. And actually, we have more than 200 cities with documented data that shows that the overheating rate is between 1 degree per decade up to, let's say, 0.1 degree per decade. The average increase of the temperature of our cities because of the global climatic change is close to 0.28 degrees per decade, which is about the double than the average increase of the temperature of our planet. So the temperature of cities is increasing more rapidly than the temperature of the whole planet. Do we have a synergy between the global climatic change and the local climatic change? Yes, there is a very high synergy. The higher the intensity of the global climatic change, the higher the intensity of the local climate or the local overheating. What I mean? I mean that during heat waves, for example, the temperature of our cities or the difference inside the city is increasing. You see, for example, here, the results that we have really analyzed, one of my students, and you see that during the heat waves, the temperature difference between the Olympic Park and the observatory is increasing tremendously compared to the period, let's say, where we don't have a heat wave. So once let's say, the strength of the global climatic change, heat waves, is increasing, the local climatic change, the local overheating is increasing as well. And this is a very risky, let's say, synergy. Is the urban heat island, the local climatic change, well documented? Yes. As I told you before, there are more than 400 cities around the world where we have multi-year data, experimental data, that shows really that the temperature is much higher than the temperature or the corresponding temperature of the surrounding areas. I'm just presenting you some data we have for Asian and Australian cities, and you may see that the average increase of the temperature of our cities is close to 5 degrees. This is very high. We have cities where the ambient temperature is to about 10 degrees higher than, let's say, the average rural temperature. You understand the impact of such a phenomenon. What is happening in Australia? What is happening in Sydney? We have analyzed the data of the last, let's say, 50 years for different months. And as you may see, for example, for the different months, January, March, and the other months, there is a continuous increase of the average temperature, not the peak temperature. And during the last 30 years, there is an increase of the average temperature up to 2 or 3 degrees. Why? We will discuss about it. But this is very well documented. It's not just the temperature increase. It's much more than that. It is the increase of the duration of the hot spells at the same time. If we try to plot the duration of the hot spells above, let's say, 27 degrees, or about, let's say, above, 40 degrees, 37, or above 40 degrees, you will see that during the last years, there's a tremendous increase. So it's not just the increase of the average, or of the minimum, or of the maximum temperature. It is also the increase of the duration of the hot spells, which is statistically significant, is important. And unfortunately, it's not just that. It is also the very high increase of the frequency of heat waves, and you see what is happening during the very last years, and also the duration of the heat waves. For example, the number of days with heat waves in Sydney, in Perth, in Adelaide, between, let's say, the years 1850 to 1980, was 6 per year. During the last, let's say, 25 years, there is an increase by 50%. It is, let's say, 9. At the same time, during heat waves in Sydney, the average temperature, the maximum temperature, has increased by 1.5 degrees, in Melbourne by 2 degrees, and in Adelaide by 4.3 degrees. So we have a phenomenon where we have more frequent, let's say, heat waves, last more, and the temperature is higher. And this is very well documented. Do we have, let's say, an important stratification of the temperature or distribution of the temperature in Sydney compared to the different, let's say, areas? Yes, everyone knows that really the eastern areas, because of the sea breeze, present much lower temperature than the western part. In this map, you may see the cumulative temperature difference for 1 year during, let's say, the summertime. You may see that in cumulative terms, Western Sydney has almost 2 or 3 times higher cooling degree days, as we call it, than the eastern part. So this is extremely well documented with a very high number of stations. In UNSW, we have installed about 25 stations, and there are many other stations from BOM and other, let's say, institutions. So we have very well documented data of what is happening in the city. I think that this is well known. It's not something that you don't know. What is really important is why this happens. Why we have this phenomena of, let's say, temperature difference between the eastern and the western. The reason is that in Sydney, we have 2, let's say, synoptic systems, as we call it. We have sea breeze that is coming from the sea, of course, and contributes to decrease the temperature in the eastern part. This is one major cooling mechanism. But on the other hand, we have another synoptic system, another mechanism, which brings air from the desert. So both systems, they fight in Sydney. And because of these specific conditions that you see, these are real data from, let's say, a heat wave day, Because of this, we have this specific temperature distribution, where the eastern suburbs present a much lower temperature and the western suburbs present a much higher temperature. Why? Because the eastern suburbs really are very much influenced by the, let's say, sea breeze, while the western, let's say, suburbs, they are influenced from the other system, the second system, and unfortunately, the sea breeze cannot penetrate, let's say, more than in the eastern part of Parramatta. Once, and this is rare, the phenomena of the sea breeze is really important and strong and became stronger than, let's say, the system coming from the desert. In this case, we may have a very strong sea breeze, and because of this strong sea breeze, we have such a distribution of the city, where really the southern part of the city is really cooler. We have a very lower temperature in the western part, but in specific areas around Perth, because of very, let's say, specific climatic conditions, temperature persists and is quite high. This is the mechanism that defines really the temperature in Sydney. Two systems that they fight between them. Given that, it is very important to understand the impact of this overheating. And there is an impact, first of all, on the peak electricity demand. We know that in the world, as an average, for each degree of temperature increase, we need to have 20 watts per person and degree, which means that the peak electricity demand, or the demand of electricity of the power plants will have to increase, it is about 20 watts per person and temperature increase, which is in reality huge. You may ask me what is happening in Sydney. This is the distribution of the peak electricity demand in Sydney during a heat wave. During the whole year. You may see that really when temperature is quite low, 15, 20 degrees, we need almost half of the power plants than when temperature is much higher, 40 degrees, which means that about 50% of our stations have not to work, have not to be, let's say, operational during the whole year, which means that the cost of electricity is increasing tremendously. A part of the very important increase of the peak electricity demand, we have an increase in the absolute energy consumption. We know that this corresponds to about 225 kilowatt hours per, let's say, person and degree, which is very high. Is it important, let's say, this phenomena of a temperature increase that increases the energy consumption? Yes. From all the data we have for specific buildings around the world, thousands of buildings, monitored in the 70s, monitored during our time, there is a continuous increase of the energy consumption, and the average increase is close to 23%. What is happening in Sydney? What's the difference of the energy consumption in the eastern and the western part? This is the distribution. You may understand that the energy we have to spend for exactly the same building in the eastern part of the city, in the western part of the city, is almost 2 or 3 times higher than the energy consumption for the same building in the eastern part. There is a huge penalty which is imposed to the specific, let's say, residents of the western suburbs. A part of the energy consumption and the peak electricity demand, we have a serious problem with comfort. If you count the number of days where comfort is above, let's say, PMV2, which means very hot, you see that there is an increase of the days above, let's say, this limit or this threshold of about 120%. So comfort and outdoor comfort is also a serious problem. However, the more important problem, it has to do with the low-income citizens and the low-income households. We know from all around the world that once, low-income household who used to live in, let's say, poor houses, they have to face a problem of overheating during heat waves. Unfortunately, this household, they don't have the, let's say, the capacity to use an air conditioning because of different reasons. And we know that during the heat waves, temperature inside low-income households is quite high, above 35 degrees. And this, this is something that is measured and documented very well around the world. What is happening in Australia? During the last year, we had the privilege, together with OEH, to, let's say, measure continuously the temperature in 100 low-income households in Western Sydney and Eastern Sydney at the same time. I will show you the results of winter. I was really surprised to see that during winter, indoor temperature may be as low as 5 degrees, 6, 7, 8. And during November, because this data report, let's say data of November, indoor temperatures for specific days could be as high as 35 degrees. Very recently, we downloaded the data of January. See the data, 40 degrees. 20 consecutive days with temperature above 35 degrees. Real data. And this brings us to the major problem we have. I've forgotten something. It's not just the high temperature. It has to do also with high indoor pollution. We measure indoor pollution in these houses. The threshold for CO2 is about 600, 700 ppm, parts per million. See the measured data, 4,000 ppms. 4,000 ppms with 40 degrees. This means increased mortality and increased morbidity. During the very last years, we have documented very well that there is a tremendous, very serious relation between mortality and temperature. So for different cities around the world, and especially in cooling-dominated climates, we know that mortality, heat-related mortality, is increasing tremendously or exponentially at temperatures between 28 to 32 degrees. It's not the same everywhere, but this is the threshold. On the contrary, in heat-dominated climates, London, Stockholm, etc., the threshold temperature over which mortality is increasing exponentially is much lower. In London, it's 22 degrees. So all those they say that, climatic change is very good for us because temperature will increase, they will face a huge problem of, let's say, mortality. Having, let's say, this data, we try to collect information, real information in Sydney and other Australian cities. And I can tell you that from real data, mortality is increasing, let's say in Western Sydney, up to 5.3% once temperature is increasing by 2 degrees. And morbidity is increasing by 6.4%. It's huge. Also, during the last 10 years, there's a tremendous increase of the average mortality and morbidity in Western Sydney. Same in Darwin. These are data from Darwin, real data. What is really very surprising is that once temperature is above 32 degrees in Darwin, and at the same time humidity is about 75%, then heat-related morbidity is increasing by 263%. I had a problem to understand and accept this number. And in Darwin, they told me, yes, during these days, hospitals are really full. So heat-related mortality is very important. Based on this data, there are models that show the heat-related mortality in different cities, including Sydney. This is the map of the heat-related mortality in Sydney. And you may see that in western part, the calculated heat-related mortality, but also, the measured heat-related mortality is 3 times higher than in the eastern part. Once you try for specific days to plot the data about heat-related mortality in the eastern part and in Perth, for exactly the same days, you will be surprised to see that it can be 3 times higher. So in the western part, because of the overheating, we have a tremendous increase of the peak electricity demand, a tremendous increase in penalty of the energy consumption, a huge problem of comfort, and a very high mortality and morbidity. The future. what really we expect for the future. This is a very nice, let's say, graph that I received from a friend recently that is official in Australia and shows the projections of different, let's say, governmental institutions. And you may understand that in Perth, they expect an increase by 3, 4, 5 degrees. This is not a surprise for us because we have run very specific simulations for 2050. And we found that really during 2050, the expected increase of the temperature in Western Sydney may be between 4 and 5 degrees. If we try to compare the temperature during a heat wave against the temperature during an average day of, let's say, 2017, and also the temperature in 2050, without taking into account the change of the land use in Western Sydney, you will understand that we expect an increase of the peak, of the peak temperature up to 4 degrees. And once, the change of the land use is taken into account, the increase will be of the order of magnitude of 5.4 degrees. You may say, it's an exaggeration. I can assure you that all models by all institutions in Sydney and Australia shows exactly the same thing. So, if you try really to plot what is happening, you will see that, for example, for 2050, we expect, let's say, an increase by 4 or 5 degrees, plus the effect and the impact of the additional, let's say, construction, the new land use, 1 degree. And this really, of course, does not take into account the heat waves of that period. This is the normal temperature. The impact of the increase of the temperature in the future. First, a tremendous increase of the energy consumption. The red line shows the actual energy consumption. 3 scenarios. Low development. Low development means that we may have an increase of the cooling energy demand by 320%. Average development, 750%. High development, 2,270%. When uncertainty is taken into account, these are the numbers. So let's be prepared to build a lot of additional power plants to satisfy this demand if measures are not taken. You may tell me, this is an exaggeration. Too high numbers. No. The scenario I showed you is the yellow scenario. These are the other scenarios published. So this is a moderate prediction. Energy consumption. Energy consumption in 2050, because of the, let's say, increase of the temperature, may increase for cooling up to 250%. Energy consumption for heating will not decrease because we have extremes as well. But the major problem, not only in Sydney, in Australia, all around the world, is the tremendous increase of the peak, let's say, heat-related mortality. This is an editorial from The Guardian that shows that, according to all estimates from the more serious people about this, shows a tremendous increase of heat-related mortality by 2050. And these are the official expectations or predictions published by 30 of the best scientists in the world about, let's say, mortality during the winter, mortality during the summer. See what we expect, for example, in South Asia or in other parts of the world. So heat-related mortality is going to be the major issue of the future. Energy is nothing against the impact of, let's say, heat-related mortality. What is happening and what we expect regarding heat-related mortality in 2050 in Sydney? Mortality, actually, heat-related mortality in Eastern Sydney is 5 people let's say, for 100,000 people. This is in Western Sydney. It's almost the double. Based on the existing climatic models, CSIRO, etc., we may go up to this level. These are the official predictions. These are the bad news. Do we have good news? Can we mitigate the problem? Can we solve the problem? Yes. We can really fight overheating. During the last 20 years, there are very, very let's say, important research carried out. Research that really tried to develop and propose several mitigation technologies. I show you some of them. Vegetation, new materials, evaporative systems, radiative cooling, control, many, let's say, technologies of, let's say, mitigation. So we have technology. Is it enough to have technology? No. First, we have to identify the problem. We cannot really proceed by using empirical methods. I heard that someone in London has applied this kind of materials. Let's do it in Sydney. It's a completely different problem. It's a completely different issue. Needs completely different solutions. So number one, and the more important issue, is to identify the problem. In UNSW, we have developed some very advanced monitoring techniques using drones, energy buses, etc. And we collect all this information. We are able to have thermal mapping 6 centimeters by 6 centimeters. This is the center of Alice Springs. So we know where the problem is, the red spots. So we can intervene and understand exactly and really face the problem, not general things. On the other hand, we have developed very important, let's say, new methodologies of monitoring, and please allow me to show you something, I hope it works, where we are able to understand and map the thermal conditions in, let's say, in cities. This is a 3D mapping of, let's say, a main street in Parramatta. This is the temperature distribution, 3D temperature distribution, made with thousands of, let's say, pictures taken by drones. And you may see that we're able to have a very good understanding of what really happens in the, let's say, in the built environment. Having this information, and once we understand the problem, we scan and we know we can solve the real problem. Otherwise, we may solve another problem. Which are the mitigation technologies? I don't have the time to go through all the mitigation technologies. First, the use of water, evaporation. During the very last years, we know that the intensity and the duration of heat waves is very much associated with the precipitation of the previous months. And these are the data. For example, once, precipitation is lower, we don't have rains, the intensity of the heat waves is much higher, everywhere. Once we have, let's say, rains, the intensity of the heat waves is lower. And this is documented all around the world. Water is very important. How much water may decrease the temperature in the city? Up to 1.9 degrees. Is it enough? No. We have an overheating of 9 degrees, 5 degrees in the future. But it is important to know it. Second, greenery. There are plans to plant 5 million trees, but what we can expect from the additional, let's say, use of trees? Important results. You may expect a decrease of the temperature up to 1 degree. This is the maximum potential of urban greenery. Is it enough? No. Where is the real research on mitigation? Materials. During the very last years, we have developed very advanced technologies based on materials. And I just show you some of them. Technologies that really contribute during the very last years to decrease the surface temperature of the city. I don't like to go through all these technologies, but actually we have, let's say, cool materials, and you see cool tiles here, exactly the same color like the conventional materials, but these materials are really reflected in the infrared, so you can see the difference. And you may have, let's say, a cool black. For example, see 2 black tiles. The one which is the so-called cool material, it has 25 degrees lower surface temperature. These materials are used almost everywhere in the world. And these materials will start to be produced now in Australia. Once these materials are used, for roofs or for pavements, temperature may decrease, the peak temperature may decrease up to 1.5 degrees. And we have more than 400 applications, large-scale applications all around the world, that shows, monitor applications that really we can decrease the temperature up to 2.5 degrees by using this kind of materials. But we have more advanced, let's say, results. We have thermochromic materials, materials that change the color as a function of temperature. Materials that collect solar radiation during the winter because they are black or any color and becomes white during, let's say, the summer. And these materials already developed in UNSW, we are doing a lot of research on it. We have developed this kind of materials, present about 20 to 25 degrees low surface temperature. If you don't believe me, just look, the thermochromic, the thermal image. These materials have some problems of aging, but we have succeeded really to solve this problem by using optical filters. There are many other new techniques, quantum dots, the minimum, let's say, the minimum size of matter, nanomaterials, but the minimum. What is happening in the micro, let's say, systems? In reality, once solar radiation or radiation falls on these materials, radiation is not absorbed. Or if you like, radiation is absorbed but is re-emitted. In this case, you don't have a temperature increase. We work on the development of these systems, and for the time being, we have succeeded really, there is a lot of work to be done, to decrease the surface temperature by 15 degrees. At the same time, we are working on new materials, new systems, like the elastocaloric systems, very advanced cooling systems, that really, because of the latent heat released when they are stressed, we may have, let's say, much lower temperatures. You see the temperature difference that we may achieve at extremely high efficiency, like you see there. Just to remind you that the efficiency of the compression systems, it's up to 3, 4, 5, the maximum. Here we may have much higher, let's say, efficiencies. But the major achievement, it has to do with some new systems, which are called photonic and plasmonic, which have succeeded to really radiate all the heat they have in the so-called atmospheric window, in the part of the atmosphere that do not absorb. In this case, this material that have been developed the last 3, 4, 5 years present much lower temperature than the ambient temperature. Just to show you a recent development, which is a plastic system, just a plastic film, which is photonic and has billion of, let's say, nanomaterials inside it. And you see, for example, this material that presents about 15 degrees below the ambient temperature under the sun. Actually, we have achieved to have materials that are about 15 to 20 degrees below the ambient temperature under the sun without the use of any, let's say, energy. We use these materials now in a pilot project in Phillip Street in Parramatta. And you see the actual, let's say, thermal comfort in this area before and the thermal comfort after the use of these materials. This is the major, let's say, development that may help us to decrease temperature. In conclusion, we started with materials, here is the surface temperature, and with materials that presented this temperature. Then we had the reflective materials I showed you, then nanomaterials, then materials, thermochromic materials I showed you before, then materials that have, let's say, a very high efficiency in the visual spectrum, and here is radiative cooling. So during the last years, we have succeeded to decrease the surface temperature of the urban fabric by 20, 25, 30 degrees. This is extremely important. Do we have enough knowledge? Do we have enough examples? Yes. During the very last years, we have more than 200 large-scale applications all around the world. And all these applications have been monitored. And we know, for example, that once we had at the beginning highly reflective materials, temperature was decreased by, let's say, 0.5 degrees. Then we developed, let's say, infrared reflective colored materials, the one I showed you, and we continuously decrease further the peak temperature of the cities. So by using the different technologies, actually, we are somewhere there. We are able to decrease the temperature of the cities up to 2.5 degrees. This is our highest capacity. By using the new materials that we work on, we expect that in the next 2, 3, 4 years, we will have, let's say, we will achieve to have a decrease of the temperature by 4 degrees, which is the real potential of mitigation in Sydney. When all these technologies, not the very sophisticated ones, the conventional one, are used, we may decrease temperature in Sydney up to 2.53 degrees. And this is very well documented. So we are somewhere here now. Unfortunately, we expect that in 2050, we will have a tremendous increase. By using mitigations, we'll be somewhere there. It will help a lot. And once we try really to plot the real potential of the different mitigation technologies, we are here. If we don't really act, in 2050, we'll be somewhere there. I'm sorry, somewhere there. And this is the heat wave. And once, mitigation technologies are applied, we'll have, let's say, this result, which correspond to a temperature decrease of about 2 or 3 degrees. And this is going to be the distribution of the temperature when these different technologies are used in Sydney. We have all possible studies. We know the real potential. Is it enough to apply these technologies? No. Why? Because let's say the magnitude of the overheating is much higher. We have capacity to decrease temperature up to 4 degrees. Unfortunately, overheating is more than 5, 6, 7, 8, 9 degrees. So what we have to do? We have to combine adaptation and mitigation. Adaptation means better building. We cannot continue with this quality of the buildings. We need to have buildings with much better thermal quality. To understand the capacity of adaptation, I will show you the energy consumption, in Sydney of a residential building today. In 2050, increase of the energy consumption for cooling, reduce the cooling by 250%. Once mitigation technologies are used, we may have a decrease up to 40%, but once mitigation and adaptation are used together, the energy consumption may decrease by 90%. So there is a tremendous potential for further decrease of the energy consumption and improvement. What is much more important is the potential decrease of the energy of the heat-related mortality. I showed you this graph before. Here is Eastern Sydney, Western Sydney, the expected, let's say, increase of the heat-related mortality by 2050. Once these mitigation techniques are used, we may be somewhere there. Is architecture and design important for, let's say, the construction of Western Sydney? We studied 14 different layouts of cities. High density, low density, high, let's say, high buildings or lower buildings, etc., etc. And once, let's say, we compare 4 different layouts, very low, high, let's say, up to high density, then we may understand there's a very important temperature increase once, several, let's say, configurations are used. And just to better understand, once we have, let's say, such a configuration, we may have up to 1.5 degrees lower temperature than when we have this configuration. Which are the parameters that define this? The parameters that define this for the same, let's say, plot area, it has to do with the height of the buildings and it has to do with the width of the streets. But this is very complicated and we will have time really to discuss later. Conclusions. First, cities, not only in Australia, all around the world, present 6 to 10 degrees higher temperature than the surrounding area. Unfortunately, this magnitude of overheating is continuously increasing. This has a tremendous impact on, let's say, energy. Energy consumption is increasing by 100%, a huge penalty, especially for low-income population. This has a tremendous impact on mortality. All around the world, we know that the future problem in the built environment is going to be heat-related morbidity and mortality. And this affects very much low-income population, as I showed you before. At the same time, we have really to build continuously additional power plants to satisfy the demand, because the additional electricity for peak electricity to satisfy the peak electricity demand is more expensive. This means that the cost of electricity will increase a lot. This is a problem. What we can do? With the actual development of mitigation technologies, we are able to decrease temperature up to 2-3 degrees, and in the near future, up to 4 degrees. We are able to decrease, let's say, the energy consumption up to 40%. We're able to decrease heat-related mortality up to 40%. And at the same time, we're able to decrease peak electricity demand by 10%. Is this something that will happen in the future? No. It happens actually in more than 400 cities around the world with real applications. Last slide. Urban overheating is not an isolated problem. Has not to be seen as an isolated problem. It is part of a global problem of our cities. In our cities, we have a problem of overpopulation. We have a problem of, let's say, increase of the boundaries, climatic change, poverty, slow technological development. So there is a challenge for the future. What is really important is to translate this challenge into opportunity. How this can be done? By to generate wealth, to increase employment, promote social equity through eradication of the poverty, mitigate the climatic change, decrease the energy consumption, improve the environmental quality. Are we able to do that? Yes. We have the technology, and we will have better technology in the future. So there is a challenge, there is a problem, but this is an opportunity. Why? Because through the necessary investments, we may generate wealth. We may translate the problem into an opportunity. But to do that, we have to work on real cutting-edge technologies. We have to stop working with myths. Once, you have someone that has, unfortunately, cancer, you cannot give him, Chinese traditional medical treatment. You need to have very strong medicals. And we have to develop really technologies together with good architecture, together with everything we know. But only those that they work on the future developments, cutting-edge developments, they will be able to develop technology. And this technology is going to be, let's say, very important in the future. The actual market up to 2050 for mitigation and adaptation, let's say, activities around the world is $100 trillion. Only those that they will develop technology, only those that they will have the know-how, they will survive. They will be able to distribute the technology and have benefits. All the rest will be clients. Thank you very much.
Matt, that was just an extraordinary presentation. So incredible to put before us, first of all, so much things that we know. It's cooler in the east than in the west, but all of that documentation, all of your research in recent years has really driven home of the lived reality of the citizens of our city and the global implications, of course, in all cities in the world. And I think what is really inspirational to us in our faculty is just how much of your work in recent years has looked at our own cities in Australia, in Darwin, in Alice Springs, in Adelaide, but above all, perhaps for our own city in Western Sydney. And what you put before us is both, in a sense, terrifying and exciting at the same time, but it's truly alarming to see those mortality rates and to see the implications, indeed, of everyday life, and in terms of simple issues to do with comfort level, outside and inside. And I think that what my first question, and we're going to have now a Q&A session, and we'll open the floor to questions, and please, throughout the room, think some marvelous questions to put before Professor Santamouris. But my first question really goes back to what we know about the future of our city and the big commitment that has been underway really since the 60s of growing in Western Sydney, and now with the decision to go ahead with the Western Sydney Airport. Just in your own researches, how do you see that playing out, and how receptive are the Greater Sydney Commission and the Western Sydney councils to the challenges and the data that you put before them of how the airport will change the land uses as well as all that we know from urban heat island effect in general?
Thank you, James. Facts are facts. We know that actually we have an overheating there, 5, 6, 7, 9 degrees. We know that unfortunately this area is very much influenced by the desert. We know that unfortunately climatic change is a reality. It's not science fiction. We know that in the future we may have a further increase there. The impact is very well documented. All these institutions you just mentioned, they know, because they have performed all these studies. There's not just one study, there are many studies around it. And they try. They try. Different activities. I think that actually we are in a procedure to understand and move from the myths into the reality. It will take some time. In Europe, it has taken 10 years to understand. The same in the United States. But I think that there is a progress. There is a real progress. Given the situation we expect, we have to build our common space in a better way with the actual technologies, with the actual knowledge we have. But what is really an emerging priority is to have better buildings. Australia needs better buildings. It's not possible, the whole world, to build zero energy buildings mandatory, and in Australia to have such a huge energy consumption and such bad indoor conditions. If we continue to build the same quality of buildings, by 2050, the penalty would be tremendous for the national economy. So I think that now it is well understood. This is, in my opinion, the #1 priority.
Yes, well, it's certainly fascinating indeed to see, for example, some of your research at the end of your presentation of looking at the different configurations of building types and the implications in all of that you've been putting before us in terms of the urban heat island effect and its effect on energy and mortality and so on. So to bring that back to building types, which is our area of urban development design, is in itself a revelation, I think, although we're finding you get this evidence base on which the studies of density and the great controversies of density in our city can be debated. And we are certainly moving into a sort of a political sphere. We're coming to elections in both state and federal in the next few weeks. These issues are clear from the research evidence, from the academic background of what a great university should contribute to public discourse and debate. The evidence, as you say, and how we must go out and, of course, move beyond myth into reality from all of the techniques that we have of measuring climate and interpreting that data. There are roving mics in the audience, and let's have some questions, please, and we'll have a Q&A session.
You spoke about a number of technologies. Do you believe that we need to mandate those for a government? And if so, have you had any inroads in mandating those?
I'd like to reply in another way. Recently, 6 months ago, the Council of Los Angeles decided to paint with a new material, which is fantastic really, all the main streets white. They said, if you visit Los Angeles now, all the main streets are white. This decreased temperature up to 2 degrees. The same happens in many areas in the States. For example, in California, it is mandatory to have white roofs. Here, we have black roofs in Western Sydney. So, in reality, in the built environment, there are two major policies. Either the country, the state, defines the boundaries and the regulations and the market follows, or the state leaves the market to do. If you leave the market to do, the result always around the world is that you have low quality and very high prices. If you have, let's say, a very good regulatory frame, like what has happened in the last 20 years in Europe, Europe was very highly criticized to do that, but it's very successful. It's a win-win, both for the market, for the citizens, and for the state. So this is a fight.
Hi, Professor. I have two questions. The first one is there any possibility that we can make heat a renewable energy? The second question is...
Can you repeat the first one? Is there any
possibility for
to make the heat a renewable energy too.
renewable energy as well, yes.
Yeah, renewable energy is very important, and renewable energy may contribute highly to reduce the peak electricity demand, and the additional power plants will contribute really to have, let's say, to relax the system, the energy system. The actual cost of renewable energy systems is really decreasing a lot, so there is a huge prospect for renewable energy sources. Attention. The use of photovoltaics in the built environment, especially in cities, increase the temperature. Why? Because the temperature, the surface temperature of the photovoltaics is quite high. They need cooling, so it increases the temperature. So we have to be very careful once we're using photovoltaics in the built environment. But in general, the use of renewables is one of the very promising, let's say, technologies for the future.
Thank you. I have the second question.
Yes.
Do you have any comments about the temperature in Melbourne? Because lately there are severe bushfires around.
You know, unfortunately, like in Sydney, the temperature in Melbourne is increasing as well. I have not presented the data in Melbourne because I didn't like really to have an encyclopedic, let's say, presentation. Temperature in Melbourne is increasing as well. The problem, you know, in the coastal cities of Australia is that the frequency of heat waves that happens because of the global climatic change. It happens because the temperature in the Indian and the Pacific the temperature of the water is increasing. And because this, let's say, heat is transferred in a very simplified way through the rosebud waves through the desert, then a very high pressure system is developed around the cities, the coastal cities, and stays there. And this increases the temperature, the duration, and the frequency of heat waves. This happens in all coastal cities of Australia. So this is a fact, and this is unique in Australia. And this happens for two reasons. First, because the temperature of the water in the Pacific is increasing, so waste heat in, let's say, in California, it has an impact in Perth. And second, because of the desert in the middle of Australia, that increases the temperature and humidity at the same time.
That's extraordinary insight and encapsulation of that complex global phenomenon. Perhaps on this side of the room, other questions? Yes, please.
First, I'd like to say thank you. I'd like to say thank you for the presentation. Very valuable information that you presented, and also good to see what the future can be. Now, my question just is about the cost of these materials, because that's also an important thing to consider. How much more does it cost to use one of these materials that reduces the temperature versus the common materials that we're using nowadays?
Yeah, thank you. Actually, you know, in developed markets where mitigation is applied, you know, almost every day, for example, in California, the cost of the mitigation materials is about 5% higher than the cost of the conventional materials. 5–10%. Depends on the average cost, you know, in the area. In Europe, the average cost of pavement is about 10 euros per square meter. I was very surprised to hear that in Australia, in Parramatta, the cost they pay to the contractors per square meter of pavement is $250. So if we pay $250 for pavements, the additional cost for mitigation is zero. Zero. So in reality also, you have to consider that the cost we have to pay in the future, if these materials are not used, or if these technologies are not used, the so-called the cost of inactivity is 25 times higher. So if we don't really invest in it, then we'll have a problem. The third thing I have to tell you is that by having new technologies, you boost the economy. If these technologies are produced in Australia and have to be produced in Australia, we boost the economy. Why? Because these materials may be produced. Because Australia is a more developed country in the area. So this is the meaning, and this was my conclusion. Let's develop technology that may solve the problem here and will generate added value. Let's translate the challenge into an opportunity. And this happens through industrial development. The development of advanced material is, let's say, such a procedure.
Well, it's certainly fascinating to see those holistic and lateral thinking connections that are possible whenever the opportunity is conceived to turn this challenge into a positive instead of the great overwhelming negative that is certainly before us in terms of the data. Right in the back of the room, at the very back of the room.
Hello, thanks. Yeah, really saddened to hear about trees not being quite enough to give us all the heat reduction we need. Is there a possibility of, I guess, mixing technology with trees, I guess having a specific tree type, or being more innovative with green roofs and that kind of thing to, I guess, bring nature and the heat reduction we need together?
Yes. But I think that you did have amongst your range of mitigation strategies, a range of landscape solutions. And did you sense that Matt was saying that wasn't viable or wasn't...
In reality, you know, everything and every kind of technology and every kind, you know, of design helps a lot. But what is important is to know the real potential of everything. If we live with myths, that we can solve the overheating by planting 2 million trees, for example, then, you know, unfortunately, we'll have big surprises. So the role of scientists, the role of engineers, the role of researchers is to document, let's say, the potential of the different technologies. You cannot fight against cancer with aspirins. You need to have the proper tools. You need to have the proper medicals. So everything helps a lot. But we have to know the potential. And I try really to give a very fair estimation of the potential. If we like really to solve the problem, we have to work together. Good design, with good technology, cutting-edge technologies, new developments, a lot of research on it, and we have to accept that we have to work on it. If we don't accept it, if we deny that the problem is here, in the future, we have to buy, let's say, this technology from the others, and the problem will not be solved.
Well, as always, it's the great challenge of all of us in the design world to move beyond our sort of conjectural, precedent-based design understandings to evidence-based design. It's been before us as a challenge for 50 years, and I still think most design professions are a long way from using the evidence instead of the models we think we can borrow from elsewhere, or we can apply from our existing experience. And perhaps we've got time for one more question.
Thank you. I've got a question about density in our cities. There's a very often increased density has been highlighted as a solution to better sustainability in our cities with waste, transport and all that. But what is the impact of increased density on the heat problem?
Usually, once we increase density, by using conventional materials, you have higher absorption of solar radiation, and you have higher emission, you have higher let's say, convection, you have a high temperature, let's say, increase. But this depends very much, on the wind flow, the orientations, and many other issues. It's not a very simple solution. You may have a higher density, and you may have lower temperatures. When really the materials used do not contribute to increased temperature, the orientation is a proper one, we'll have the proper solar control and shading, and we'll have the proper ventilation. So it's not just density that contributes to increased temperature. It is density in combination with many, many other, let's say, parameters. I didn't have the time to present you the results of the 14 different, let's say, layouts we have analyzed. You see the layout here.
This material is really fantastically interesting.
Yeah, and sometimes I was surprised really to see the results. It's a very complex issue. There is potential here. We may decrease, let's say, temperature, the future temperature, of future settlements up to 2 degrees by proper design. This is very important. And when, let's say, proper mitigation technologies and adaptation technologies are used, we may have in 2050, despite the temperature increase, zero energy buildings with very low, almost zero energy consumption. It is possible. Actually, we have designed and built 4 settlements in Europe, in Cyprus, Italy, France, and the UK, of zero energy consumption built. And what is important is by using these technologies, we have decreased the cost of the settlements by 16%. Why? By using, let's say, community-integrated energy systems than building-integrated systems. So the message is clear. We know how to do it. Technology knowledge is here. And it's a complex phenomenon. But this one has to be, let's say, demonstrated. So first, let's have some demonstrations. Let's show to the people that it is possible to decrease temperature to have better buildings. Once the Australian people, which is very progressive, understand it, feels that, then there will be a boom. We need some, let's say, demonstration on it.
I guess on that note, Matt, I think it's a great one to end on. This is right at the center of our area of urban development and design. And it's just been a very stimulating Q&A. I thank everybody who's asking the questions. They brought up a lot of other added dimensions to what was already a marvelous presentation. So, Matt, we truly thank you. It's been a great pleasure to have you. Before we go, I'm just going to talk to you just briefly about what our students have been doing this year. It's been a very exciting year, the 24th year of the MUD program. We've done 50 and 51 international studios in that time. This year we went to Boston for the 2nd year in a row, hosted by the great multidisciplinary firm Sasaki Associates, who welcomed us back for this year as well as last year. We looked at the land that Harvard University has acquired across the Charles River in Allston, in the city of Boston, 110 hectares of former railroad yards, and involves moving the Mass Turnpike and building a new railroad station. And it's, of course, in tune with our theme of urban networks and urban gateways. And I was joined by Michael Giorgio as tutor on that, and I truly appreciate Michael's great support in all of our design studios. Our second international studio was in Japan. We've returned to Japan some years. We were in Tokyo way back in 2007 and Nagoya in 2009. High time we went back to Japan, and this time to Fukuoka on the southern island of Kyushu, which is a booming city in Japan because of its proximity to Busan in South Korea, and of course all of the great cities of China, coastal cities of China. And there we looked at the classic waterfront challenge. And I really thank my colleague Brendan Randalls and also Jun Sakaguchi from Jackson Tees, who took our students to work with the Graduate School of Design at Kyushu University, who are wonderful hosts for us, and our students could work with the Japanese students in that great interdisciplinary cross-cultural setting. Our Studio 2 this year is really the theme that brings Matt to the lectern this evening. So my colleague, Dr. Scott Hawken, has done a wonderful year-long study at Western Sydney linked into the International Geodesign Collaborative organized by Emeritus Professor Carl Steinitz from Harvard Graduate School of Design, where 80 universities worldwide have been looking at the challenge of climate change within their own cultures, within their own climatic zones and so forth. We were the only university from Australia to participate in this, and our work is on display now in California, and it lays out in many ways alternatives for Western Sydney, for the Aerotropolis, which will be an international gateway for our entire nation, with all of the challenges that Matt has put before us on how to deal with the extraordinary urban heat island effect and climate change that's associated with the bigger climatic movements worldwide. Our Studio One, which I directed again with Michael Giorgio and Amy Bendel and my other colleagues, looked at a classic transit-oriented development issue to do with the Southwest Metro and perhaps, for example, how Canterbury could change with the densities that are being proposed, and we came up with very interesting and provocative explorations of those ideas. So urban networks and urban gateways has been our theme, both literal ones and, in a sense, metaphorical ones, what a future university might be like, and our friend Sasaki Associates and Dennis Pipers and his colleagues wrote beautifully for us in our yearbook. And so all of this is, in fact, on display downstairs and in the Built Environment Gallery and documented in our yearbook. We're delighted for all of the sponsors that we've had who have made this possible, but there is, in fact, a blank page for more sponsors if you would like to join us and increase the print run of this 192-page magnificent publication with many scholarly articles as well as all the work of our students. It's a ISSN number. It's deposited in the National Library. We're very proud of all the yearbooks we've produced over the years. And so I must thank my colleagues, Dr. Hawken, my full-time academic colleague, all of the wonderful staff members who make it possible to deliver our program. And I'm going to just single out two very special people as conveners of the communications course that have made this possible. Andrew Sweeney, architect of this city, who works so diligently, closely with our students and works on the words and the expression of the complex ideas. But above all, I thank Jodie Lawton, our wonderful graphics expert who makes students really excel in the time that they're with us. And above all, of course, as the Dean has said, our number one thanks is to our students, our MUD 24 students, most of them in the gallery up above us. Everybody please join me for a great clap for the work of this graduating class. So the next, there will be another Utzon before August. It will be announced. I think Walter Hood is coming here in May. But we do know that in August there will be a very important event, an annual event now that Professor Lockhead has organized, the Engaging Women in the Built Environment, which is a path-breaking and truly extraordinary evening. We thank our sponsors once again for making this evening possible.